Everyone, welcome back. Today I'm going to explain a problem on deflection. A simply supported concrete beam of span 8 meter and rectangular cross section 125 mm wide and 250 mm deep is pre-stressed by a single cable in which the total tensile force is 220 kN. The center line of the cable is parallel to the axis of the beam and 75 mm above the soffit over the middle third of the span and curved upward in a parabola over the outer third of the span to a distance of 75 mm above the soffit at the supports. If the modulus of elasticity of concrete is 35 kN per meter cube and the density of the concrete is 24 kN per meter cube, calculate the upward deflection due to pre-stress only, the deflection due to pre-stress plus self-weight, the magnitude of concentrated loads placed at 1/3 point of the span, which could result in limiting short-term deflection of span 500 mm. Here, first of all, they have given the length of the beam is 8 meter and cross section is 125 mm wide and 250 mm deep. It is having a single cable which is having a tensile force of 220 kN, and about the cable profile you should pay some attention here. It is quite different. That is, the center line of the cable is parallel to the axis of the beam. That means the complete length of the beam is not complete length of the cable is not a straight line. It is not at all parallel to the axis of the beam. Only the center line of the cable is parallel to the beam. Okay, this part is important. And 75 mm above the soffit over the middle third of the span. Middle third of the span means it is nothing but L by 3. Here L may be anything, but here L is 8 by 3. At 8 by 3 distance from the soffit up to the cable, it is 75 mm and curved upwards in a parabola over the outer third of the span to a distance of 175 mm. See, only at the center of L by 3 that portion will be horizontal. Afterwards, towards right and towards left of that line, there is a parabolic variation. And till where it has got extended? It has got extended up to 175 mm. Okay. If the modulus of elasticity of concrete is 35 kN per meter cube, density is 24 kN per meter cube. These things we can write it down on, and we can identify the data also. But here the important thing is all about the cable profile. That is one thing, and these things need to be found out. So let me show you the diagram. Here, according to the given data, we can write a diagram like this. It is a beam carrying 2-point load. Here you can write it as W as well as W here. The complete length of the beam is, I have generally denoted that as L, and the cross section is like this. That is 125 mm is a width and the depth is 250 mm. Exactly at the center the neutral axis will be present. So 250 by 2 will give you 125 mm. At 125 mm distance, neutral axis will be present. And about the cable profile, the cable profile is like this, but you just go and check back here. You can see that the center line of the cable is parallel to the axis of the beam. So it is understood that from here to here this is center line, from here to here it's a straight line, this is parallel to the beam axis. That is over, and 75 mm above the soffit over the middle third of the span. They are talking about this. So from the bottom up to the cable it is 75 mm, and the curve upwards in a parabola over the outer third of the span to a distance of 175 mm. They have clearly said that from the outer side of the outer side of this cable, that is this side as well as this side, from here to here it's a parabolic variation, again from here to here it's a parabolic variation. Like this cable profile will be there, but they are also telling that this cable will end at a distance of 175 mm from the bottom. So 175 mm at the from the bottom to the support means I have just divided 125 plus 50 will give you 175. So I have written 175 here 125 here and 50 to the remaining portion. Okay, like this we can write a diagram, and also the eccentricity from the neutral axis or the value between the neutral axis and the cable is 50. Okay, how did we get this 50? 125 mm minus 75 will give you 50 mm. 50 mm exactly below the load. Again here 50 mm exactly below the load. And these are the pre-stressing forces. And about the length, they had said that, see here, middle third of the span. So middle third means complete length of the span is L, L by 3 here, L by 3, L by 3. Like this we should divide and we should write the diagram. L is 8 meter. See here it is 8 meter. That means L by 8 by 3, 8 by 3, 8 by 3. This is a cable profile. Next is a calculation of I, moment of inertia and dead load of the beam. Why do we require this dead load and moment of inertia means, see here we should find out the deflection due to dead load. That is, the always deflection is affected short term, either it may be a short term deflection or it may be a long term deflection. Always those two deflections are affected by the deflection due to dead load, deflection due to live load, and deflection due to pre-stress. So the first thing what we should do is, we don't know how much is a live load here. It is unknown. It is W here, it will be W here. But we can find out how much will be the dead load. So for that we have a formula. Deflection due to dead load is delta DL equal to 5 by 384 into WL power 4 EC into IX. Okay, so here in this formula, and one more thing, how did I choose this formula is, it's a dead load calculation. Dead load means it is a self weight, and dead load will be present throughout the beam. So throughout the beam means it is acting something like a UDL. So it is like simply supported beam carrying a UDL. If it's a simply supported beam carrying a UDL, then formula is 5 by 384 into WL power 4 by EC into IX will be the formula. In this formula you can observe W is not known and I is not known. Other than that, everything is known. Length is known, Young's modulus of concrete is known. So we should find out this W and I. I for a rectangular cross section or moment of inertia for a rectangle is BD cube by 12. B is 125 into depth is 250 cube by 12, that will be equal to 162.76 into 10 power 6 mm per 4. This is I value. Next is about the W, that is dead load of the beam. We know that how to calculate this dead load of the beam. It is cross section of the beam into density. So cross section of the beam is, here we have got 125 mm. Just convert that it into meter. It will be 0.125 into 0.25 into density is 24 kilonewton per meter cube. So take 24 equal to 0.75 kilonewton per meter is a dead load of the beam. That is nothing but W. So substitute in this place, that is instead of W, you just in place of W just substitute this 0.75 and be careful with the units. If you are converting this kilonewton per meter to Newton per mm, also it will be 0.75. There won't be any changes because from kilonewton to Newton it is 10 power 3. From meter to mm it is 10 power 3. So 0.75 into 10 power 3 whole divided by 10 power 3 will be, obviously it is 0.75. So 5 into 0.75 into length is 8 meter, convert that it into mm. So it is 8000 power 4 by 384 into 35 into 10 power 3 into 162.76 into 10 power 6. So deflection due to dead load is 7.02 mm. Okay, this is how deflection due to dead load is calculated. Here these two loads are unknown. We will calculate these W value or point load values at the end of this problem. For deflection due to pre-stress, how did I take this rectangle section is, go back to the previous diagram, that is we have a cable above the neutral axis, that is for that portion it is almost like a straight cable. So for that portion it is a rectangular section, and about the sign you just focus on the sign, that is this portion of the cable is present above the neutral axis, so it is positive bending moment. So PE1, that is complete length of the beam is L, half of that is L by 2 and height will be P into E1. Here E1 is this value, that is 50. Whatever value is there above the neutral axis, that is considered as E1. So P into, convert kilonewton to Newton, 220 into 10 power 3 into 50, we will get PE1 equal to 11 into 10 power 6 Newton mm. Here why did we calculate this value is, in further substitution in further formula we will use this value, so directly that time I can consider this value, so I just calculated. Next you can see a variation like this. How did I get this bending moment variation? That is, whatever I have written a bending moment diagram, it is for this portion, that is whatever is present below the neutral axis from this point up to here, whatever portion is there, for that portion, I have written a bending moment diagram. If the cable is present below the neutral axis, then it is a negative bending moment. Okay. So for that, we have a parabolic variation, we have a straight line, and again parabolic variation. We should consider half of it. So if we divide half of it, will be a parabolic area and one rectangle area will be there. Here, be careful while calculating. See the length. The length is L by 3, L by actually L by 3 is from here to here, it is L by 3. Again, half of this will be L by 3 by 2. That will be L by 6 equal to 1333.33. So don't get confused. From here to here, it is L by 3 only. But if we consider half of that, it will be L by 6 equal to 1333.33. Fine. Next, it is a centroidal distance. Okay, I will talk about the centroidal distance later, but this P into E1 plus E2 is important. Here, make a note that this cable profile is having two type of a eccentricity, that is E1 as well as E2. So the E1 value is the whatever eccentricity value which is present above the neutral axis. E2 value is whatever value which is present below the neutral axis and between the cable and the neutral axis is E2. Now this one is E1, this one is E2. When we are writing a maximum bending moment, at that time P into E1 plus E2 should be present here. Okay, like that we should consider for a calculation. So I have written P into E1 plus E2 has a maximum bending moment here. Now find out how much is P E1 plus E2 is. It will be 22 into 10 power 6 Newton mm. Next is the calculation of deflection due to pre-stress. Okay. Deflection due to live load is not there. Deflection due to pre-stress is there. So we should consider three areas here for the calculation. Which are those three areas? That is, one is rectangle, one is parabola, and one is rectangle. So let's start like this. First of all, general formula is delta equal to area into centroidal distance by EI. So EI, I have taken it as a common, I have written outside. So 1 by EC into I value you should substitute it here into area into centroidal distance of that diagram. So if I am considering this diagram has a first area, so area will be B into D. Here B is L by 2. So if we consider that, it will be PE1 into L by 2 as a area, and centroidal distance of this is half of it, half of the length. So it should be measured from the support. So it will be L by 2 by 2, that is L by 4 is a centroidal distance from here to this point. So like that I have substituted in the formula. So see here, this is area, PE1 is 11 into 10 power 6 into L by 2 into L by 4 value I have substituted. Next is and the important thing is here it's a positive bending moment. So here it's a positive value here. Next it is about these two areas. Which one I have considered is, I have considered rectangle has a second diagram. So for that, For a rectangle, it is B into D. Here, how much is B? It is L by 6 is a B value. That is, understand properly, from this point to this point, it is L by 3. We are taking half of that, so it will be L by 6 equal to 1333.33 is a B value, into D is P into E1 plus E2. So I have calculated here, I have substituted B into D for a rectangle into the centroidal distance. Centroidal distance is, first of all, half of this length. What is the length of this? Or yes, what is the length? It is L by 6. Again, half of this will be L by 12 plus, from here to here the value is over. Next, it is a remaining length. We should measure the centroidal distance from the support up to the center of the area. So from here to here we have covered, and the remaining length is 2666.66 is a remaining length. So take that and substitute it here. Don't get confused by looking at this. L by 6 is already calculated, so I have substituted in numerator. In denominator, it is again half of this, so it is by 2. Okay, plus length, the second area is over. Now the third area is parabolic area. We know the formula for parabolic is 2 by 3 into length into height. So what is the maximum height? It is P into E1 plus E2. I have substituted here 2 by 3 into length is 2666.66 is a length, area is over, and its centroidal distance. Centroidal distance should be measured from the support, so it is 5 by 8 into this length substituted, and be careful with the signs and don't forget to substitute these signs, as it's a negative bending moment. Why did we get this negative bending moment? As cable is present below the neutral axis, it is negative bending moment. Substitute those negative signs here. Delta PS will be minus 13.16 mm. Now we can see that deflection is upwards. Okay, so the next thing is the final calculation, that is whatever they have asked in the question we should calculate. I will just go back to the question. The first question is the upward deflection due to pre-stress only. Just now we have calculated deflection due to pre-stress. How much we got? We got in negative, that is minus 13.16 mm. This is a upward deflection. So they are asking about that. So directly write the value, that is 13.16 mm is a upward deflection. No need to write the sign here. Upward deflection means it is understood, it has come in negative sign. The second one is, what is the second point? Second point is the deflection due to pre-stress plus self-weight. Deflection due to pre-stress and self-weight means, self-weight itself means dead load. Now deflection due to dead load has been calculated, deflection due to pre-stress is calculated, so add both the values. Deflection due to dead load is 7.08 minus deflection due to pre-stress is minus 13.16. We will get minus 6.14 mm as a deflection. Next and the final question is the magnitude of concentrated load placed at 1/3 point of the span, which could result in limiting short-term deflection of span by 500 mm. Now we should take a span by 500 and we should find out how much is a concentrated load value. So for that, what we can do, see here, deflection, it should be due to, sorry, okay, deflection due to dead load plus live load plus pre-stress equal to span by 500. Okay, they have told us to use span by 500, so take that condition. Deflection due to dead load is 7.02. Please note there was a typing mistake, so I have corrected. It is 7.02 is a deflection due to dead load. Plus, what is this formula is, they have asked a question that two concentrated point loads are present. For that, this is a formula. Simply supported beam carrying a two concentrated point load, formula is this one. Write down that, minus pre-stress value has come in terms of negative, so minus 13.16 equal to span by 500. Now let us substitute all the terms which we know, that is EC we know, IX also it is known, only W is unknown, length is known, so substitute everything. Span is also 8 meter, so 8000 mm, W is 6940.2 Newton. Okay, 6940.2 Newton is a W value present here. Hope you have understood this problem. This is how we can calculate upward deflection or deflection due to dead load and pre-stress, and if they give any condition we can use that and we can find out a load. But you should be thorough with the formulas, different condition, different formula. If you are thorough with those things, you can solve a deflection problem. It's quite easy. Okay, thank you.